This is a lesson on magnets in the beginning of a unit on magnetism. I wanted to take a lecture to go over key terminology, some history, and some core ideas that will follow us through as we move further into understanding magnetism. I wanted to start with a bit of history and facts about magnetism. It was discovered in Magnesia, which is ancient Greece or Western Turkey in that area over 2,000 years ago, and there's some rocks there that exhibit magnetic properties. And the legend is metal parts of a shepherd's shoes and staff were stuck to a rock. That's the experience the person had. It turned out that rock was magnetite, or more commonly known as lodestone. And that can be the simplest evidence that there is magnetism, is to sprinkle some sort of metal iron pieces, typically on a still pool of water over a ferromagnetic rock. And what you will see is those iron filings will form a pattern. And there's no magic there, right? This is an invisible field. And I think that's one of the coolest things about magnetism and also electricity or electric fields, is that we can't see them. As human beings, we like to think that we can see everything. But these effects are at a small level that are invisible to the eye, and making them come alive and seeing them in everyday life is a sort of enchantment, it seems like to me. Even the terminology of magnetism comes from its use in everyday that we can't see. And to be honest, who knows how long on the planet the property has been known, because the terminology north and south comes from the use of the property in navigation. And humans have been navigating on the planet for hundreds of thousands of years. So I think this just goes to show how apparent magnetism is if you're aware of it and know how to use it. And modern days, applications are numerous in technologies. This is how electric motors work, generators, MRI uses high magnetic fields, computer circuits. There's elements in circuits that use magnetic fields, and computer memory is based on magnetism. Very interestingly, they're the cause of auroras in the atmosphere, and that has to do with the Earth's magnetic field, which helps navigation. And that's what the background is here. The particles, solar particles, come in and they interact with the magnetic field of the Earth. And we can't see the magnetic field of the Earth, but as soon as these high energy particles come in, we see the magnetic field of the Earth having an effect on these charged particles. And so for me, magnetism is such an enchanting topic in physics to study. So let's talk about where magnetism comes from. And I'm going to talk about magnetic dipoles. So there's some terminology you'll see come in here and some key ideas. All magnetism is created by electric charge in motion. And I have two examples over here from the OpenStax College physics text. The first one here is an atom. And this is the most basic atom. You can see a hydrogen atom here, a proton, and an electron. And so the electron is moving around the atom. This is a planetary model, which isn't accurate, but we think about the electron having angular momentum, exhibiting simple harmonic motion, moving around the proton here. And as such, it's a charge in motion. And so the atom here will exhibit a magnetic field, and that's what we call a dipole. You can see the north and south poles here, and the magnetic field is represented by these loops. Okay, so that's the basic idea of a magnetic dipole, is a north and a south pole. The electron itself, notice over here, this is just the electron itself. The electron itself is a charged particle, and this charged particle has spin. If you're familiar with spin, you know electron has spin, and so the electron has its own magnetic dipole moment. So particles, molecules, current configurations, any current configuration, you can think of an electron going around a proton as a current configuration. This is a current configuration. It creates a dipole and have what we call dipole moments. I'm not going to get much into this in the next few lectures, but the magnetic dipole moment of an electron is given by this value. You can see that the basic charge is in here, the mass of the electron is in here, and the angular momentum of the electron is in here as well. And that has to do with quantum numbers, and I'll get to that in a future lesson. The magnetic dipole of a current loop, if I just take a wire and I shape it in a circle and I put a current through it, that would have a magnetic dipole moment. And so we're going to think about how does current create magnetic fields. And you may already be thinking in your head that there are currents around me everywhere. There's currents, ions in my body. Does that mean there's magnetic fields everywhere? Yes, they're everywhere. These forces are so small, and remember, compared to the electric field as well, these forces are so small that they're not apparent to us on a gravitational level, our everyday sort of face of the planet, our everyday visible world, because they're so small and invisible. But they're there. They're absolutely there all the time. Another fact here is that magnetic monopoles do not exist. You can see I have this current here, and whenever there's a current, there's going to be a dipole. Monopoles do not exist. There are people who write whole Ph.D. theses on trying to find a magnetic monopole out in the cosmos someplace, and there's a lot of null evidence on that. So no North Pole or South Poles exist in isolation. That is a fact. Poles are always found together, okay? I chose this picture from the OpenStax text in order to exemplify that. You can see if I take a magnet that has a North Pole and a South Pole and I divide it in two, you can see that I get two smaller magnets with North and South poles, and I divide that and North and South. You can't just take the South and divide it off from the North. That's not possible. Magnetic monopoles do not exist. If you try to cut it, you're just going to get another North and South. So now that we've established some facts about how magnetism works and thinking about North and South poles and the magnetic fields, let's talk about how magnets happen. So a magnetic domain is a small piece of material where magnetic dipoles are aligned. So you can see that over here in this picture A, there's a bunch of magnetic dipoles and they're not aligned. But the atoms in the materials act like small magnets, and you could see maybe that if I take a couple that are right next to each other and they have some sort of effect on each other, they will line up and I will get a magnetic field, a larger domain, and they'll kind of clump together. Okay, and overall, when you get a larger domain, that larger domain will overpower a smaller domain, and you can see that at some point all of these atoms, all of these domains will be clumping together. Okay, atoms act like small magnets, and these, I'm talking about a scale of billions of atoms, and these regions are millimeters in size. Okay, so thinking about a piece of iron, that's what's going on in there. Those iron atoms have such a large magnetic dipole moment, each of them, and they affect one another, and we'll get into magnetic forces in a few lessons, and they affect each other and they cause each other to line up. Okay, so that's how rocks become magnetized. Permanent magnets are when the domains grow and align on a larger scale and they remain magnetized over time. Okay, there's different types of magnetized materials, and we'll see that in the next slide. But a permanent magnet, by definition, will not lose its magnetism. Those atoms are so magnetized, they will align up and at some point just have their own magnetic field in that material. So that's how magnetism can happen in a naturally magnetic material. Strong regions of magnetic domains can cause magnetism. So if I take something that's very strongly magnetized, a very strong permanent magnet, I can rub it next to another less magnetic material and then go through this whole process again of getting all of the domains to line up. So this outer region of large magnetic field will have an effect on the other region, and it will all line up as well. So you're seeing how strong this magnetic force is. On an atomic level, this force is causing the magnetic dipole moments all to align with one another. Very fascinating occurrence in nature. Continuing on how to make magnets, you can also apply high heat. And this may already be familiar with you. I like to think about the center of the Earth. The reason that humans know that the center of the Earth, that the magnetic field of the Earth has rotated through the years, is that they've studied the layers of magnetism in the sea floor. In the seafloor, as magma comes up from the center, it's hot and its magnetic domains are all random. In the seafloor, as magma comes up from the center, it's hot and its magnetic domains are all random. And in the magnetic field of the Earth, those domains will line up. And so it's been observed through the years, we're talking about billions of years here, right? That the magnetic field of the Earth has rotated back and forth. It oscillates, actually. That's how you can create magnetized material as well. Here's an iron bar. We can apply high heat in the region of an external magnetic field. Notice that there's an external magnetic field here as well. And so we get a magnetized material in between. So there's different types of magnetic materials. Not all atoms are created equal, and this has to do with filling electron shells, interestingly enough. And I'm not going to go into the details of that. What I will cover is a few vocab words here. Ferromagnetic means exhibiting strong, permanently magnetic effects, and we saw that on the previous slide. There's some materials that are just very naturally magnetic. Their magnetic dipole is very strong, and that material will stay magnetized over time. There's what we call paramagnetic, and that's the picture here. This is paramagnetic. And what happens is, in the absence of an external magnetic field, the dipole moments are aligned randomly. When you put it in the presence of a magnetic field, then those dipoles will align. And maybe it sounds a little bit mysterious how that would happen, but it happens everywhere. And the most simple example I have of this is when you take a magnet and you put it on your refrigerator. That refrigerator is not magnetic to begin with at all. You cannot take a paper clip and put it on a refrigerator. You cannot take two paper clips and get them to stick together without another magnet nearby. But once you put a ferromagnet nearby, a magnetized material nearby, you will see that within that metal, you can get the dipoles to align. It becomes magnetized. When you remove the permanent magnet, it will go back to randomized. You could imagine having a string of paper clips where you have a permanent magnet and you put one paper clip and then put another paper clip at the bottom of that paper clip. That original paper clip isn't permanently magnet, but in the field of that permanent magnet, it becomes magnetized. So demagnetizes when the field is removed. So there are materials like this everywhere in our everyday life. Finally, here is just an interesting thing, the diamagnetic materials. Diamagnetic materials repel magnets at very cold temperatures, and you can see that in the picture over here. This is a magnetic material, and you cool off this down here. I say one way because you can imagine a situation where you can arrange some norths and souths and then get some levitation just by repulsion there. Okay, so we're getting an idea about these dipoles and magnetic fields, and I've shown you a picture of magnetic fields already, but let's think a little bit more deeply about them. We can start with the idea that magnetic poles interact with one another, and you can see that in this picture over here. Opposites attract, so the norths and souths will be attracted to one another, and if you're familiar with magnets, they stick together, and also likes repel, and that can be a familiar experience for people. The North Pole on a compass, this is an interesting thing. If you think about norths being attracted to souths, what we call north is actually the fact that the North Pole on a compass is attracted to the South Pole. So that's why we call it the North Pole, is because on the compass it's the North Pole. But actually, what it points at is the south magnetic pole of the Earth, which is near the North Geographic Pole. That's how the North Geographic Pole got its name. Not that this is the North Pole magnetically, but that this is what is attracted, the side that's attracted on the compass. The units of magnetic field is Tesla, 1 Tesla, and you can see in here there's a charge, and this looks to me like a velocity, moving charge with a force in here. There's an amp, that's definitely a current. And so that's the SI components of that unit that has been combined together as the Tesla. Of course, magnetic fields, it is a field, so it will have all properties of fields, which has all properties of vectors. The compass always points the direction of the magnetic field at that point in space, which is tangent to the line. So if I go back to a picture of the Earth here with the magnetic fields on here, you can see that a line tangent to these curves at any point. And this should be familiar to what you experience with electric fields when we covered electric fields. Finally, I wanted to cover Earth's magnetic field because I've talked about it a few times, and it's our environment right here. It turns out the magnitude of the Earth's magnetic field on the surface is 10 to the negative fifth Tesla. You can see that 5 times 10 to the negative fifth. And it varies depending where on the planet you are. It's stronger at the top and at the bottom near the poles rather than along the equator. It's generated by the circulating liquid within the core. Earth. The shape and size are not the same on the sides facing away and towards the sun. And so that's the picture I have up top here. Because the sun is blasting solar particles, solar wind at us, the shape of the Earth's magnetic field changes in response to that here. It contains particles mainly from the solar wind and extends into a space you can see, and already you're imagining that magnetic fields extend way past our bodies, way past the Earth's surface. Magnetic fields are not visible and they extend far, just like electric fields. An interesting thing then that happens is the energetic electrons and protons, components of cosmic rays, whatever's in there, from the sun and deep outer space often get caught in, and you can see that these particles come in and they're just moving along and they get caught by the Earth's magnetic field. What you can see is that these moving charges spiral along the magnetic fields of the Earth, and in spiraling they release energy. Their energy is dissipated, and instead of crossing them, they get caught and brought into closer to the surface of the Earth. And again, that's where the auroras come from, is the charged particles spiraling along the Earth's magnetic field and releasing energy in the form of photons in wavelengths that we can see. So very enchanting, very cool.